Welcome to AI Unpacked, where we break down the latest in artificial intelligence. Today, we're diving into a topic that challenges current paradigms, the idea that small language models, or SLMs, are the future of agentic AI. Agentic AI systems, which allow AI to perform complex tasks by breaking them down and using tools, are seeing meteoric growth. Historically, these systems have heavily relied on large language models, LLMs, for their foundational intelligence. But our guest today, Dr. Sophia Martinez, a renowned science communicator, is here to explain why a shift is not only possible, but necessary. Dr. Martinez, it's a pleasure to have you.
Thank you, Stella.
It's a pleasure to be here. Our recent research, detailed in the paper Small Language Models Are the Future of Agentic AI, posits a strong argument. For the vast majority of tasks within agentic systems, SLMs are inherently more suitable, sufficiently powerful, and significantly more economical than LLMs. This isn't just a technical refinement. It's a call for a more sustainable and cost-effective approach to AI deployment. We believe that acknowledging the distinct roles and capabilities of SLMs can revolutionize how we build and scale AI agents, making advanced AI more accessible and environmentally responsible. That sounds like a monumental shift, Dr. Martinez. Before we delve deeper, could you clarify what distinguishes an SLM from an LLM in this context? And perhaps more importantly, how can small models possibly compete with the perceived power of large ones, especially for complex agentic tasks?
Of course, Stella. For clarity, we define an SLM as a language model that can practically fit onto a common consumer electronic device and perform inference with low latency for a single user. An LM, conversely, is simply any language model that doesn't meet those criteria. The small in SLM doesn't mean less capable for agentic tasks. In fact, modern SLMs, like Microsoft's Phi 2 or NVIDIA's Nemetron H series, demonstrate performance on par with LLMs many times their size in areas critical for agents, such as common sense reasoning, tool calling, and instruction following. They've achieved this through advanced training and architectural innovations, proving that capability isn't solely tied to parameter count, especially when models are specialized for specific functions within an agent's workflow.
That's truly impressive. So, beyond performance, you also highlighted the economic benefits. In an era where AI infrastructure costs are soaring, this is particularly relevant. Can you elaborate on the significant economic advantages SLMs offer for agentic systems?
Absolutely, Stella. The economic argument for SLMs is compelling. Serving a 7 billion parameter SLM can be 10 to 30 times cheaper in terms of latency, energy consumption, and computational operations compared to a 70 to 175 billion parameter LLM. This translates directly into lower operational costs and the ability to achieve real-time agentic responses at scale. Furthermore, SLMs enable more agile fine-tuning. Techniques like LoRa allow developers to add new behaviors or fix issues in GPU hours, not weeks, which is a game changer for iterative development. They also facilitate edge deployment, meaning AI agents can run locally on consumer devices, reducing reliance on expensive cloud infrastructure. This modularity, combined with efficient parameter utilization, makes SLM-first architectures the most cost-effective and sustainable path forward for agentic AI.
The operational flexibility and cost savings you describe are a strong case, Dr. Martinez. It also seems to hint at a more diverse and adaptable AI ecosystem. How do SLMs contribute to this flexibility and allow for more specialized or heterogeneous agentic systems?
That's a key point, Estela. Due to their smaller size and lower training costs, SLMs are incredibly flexible. It becomes much more practical and affordable to train and deploy multiple specialized expert models for different agentic routines. This agility enables rapid iteration, adaptation to evolving user needs, and compliance with local regulations. This flexibility also fosters democratization. More individuals and organizations can participate in developing AI, leading to a wider range of perspectives and potentially reducing systemic biases. Agentic applications, by their nature, often expose only a narrow, specialized subset of a language model's capabilities. They break down complex tasks into simpler subtasks, making SLMs, which can be precisely fine-tuned for these specific, repetitive functions, a perfect fit. This leads to inherently heterogeneous systems, where different models, some large, some small, can work together optimally.
It's clear there are compelling advantages. However, I imagine there are also strong counterarguments or barriers to this widespread of option. What are some of the main challenges, and how can the industry navigate them? Indeed, Stella. Two main counterarguments often arise: that LLMs have superior general language understanding due to a semantic hub, and that their centralized inference will always be cheaper due to economies of scale. We rebut these by showing that architectural innovations and fine-tuning make SLMs highly effective for specific tasks, and that recent advancements in inference scheduling are making distributed SLM deployments increasingly cost-effective. The real barriers are more practical. The massive upfront investments in centralized LLM infrastructure, the industry's reliance on generalist benchmarks for SLM evaluation, and a lack of popular awareness. To overcome these, we propose an LM to SLM conversion algorithm involving secure data collection, task clustering, and specialized SLM fine-tuning. This methodical approach allows for a painless transition, ensuring performance while embracing the economic and sustainability benefits of SLMs, ultimately guiding us toward a more efficient and responsible AI future.